Well, good morning.
Morning.
Morning. All right. Last time we talked about weak statement of elasticity, chapter 7. We are a little bit more halfway through, and then I'm going to continue the discussion and finish the rest. Okay, for this chapter. So just briefly review what we talked about last time. Very brief review of elasticity. We talk about the balance equation, force balance, which is sigma ij, j plus bi equals 0. So this is balance or equilibrium. And then we talk about stress. We talk about strain displacement relationship using the shorthand notation ij indexes, and also comma means partial differentiation. Okay. This is equal to ui, j plus uj, I. So this is the strength displacement relationship or geometric relationship. And then there is the relationship between stress and strain. In general, we can write it as Cij KL and then epsilon KL. This is the constitutive law. Okay, and again, whenever you see two indices that are repeated, that appears twice, that means summation. Okay, so this will means 1, 1, and then plus the same expression 2, 2, and then plus the same expression where this is 3, 3, like that. And again, this LL is the same thing. Therefore, that expression actually includes two summation signs in front. The index runs K from 1 to 3 and L from 1 to 3. And these I and J themselves, there's no summation because there's just each index appears just once. But each index itself can be 1 or 2 or 3. These are called the free index. Okay? So this is a free index. This is a free index. Just like I here is a free index. J a free index. But K, when they are repeated, they are called dummy index. Any dummy indexes indicate summation. So that's the convention. Okay? The reason we introduce this convention is to make it make the writing much more concise and just focus and that enable us to focus on the physics itself, not a long expression. Okay? And then the boundary conditions, we have ui equals ui bar. That's on displacement boundary condition. We call it S sub u. And then sigma ij is equal to fi is equal to sigma ij and j. That is on as, do it this way, sigma ij and j. And these give the traction along I direction. We went through derivation last time. It should be equal to whatever is prescribed on the boundary, which is SF. Okay? So this is the essential boundary condition. Let me write it using red pen. This is natural boundary condition, right? And any parameter or variable, any parameter with a bar on top means is a given value. So we know these values. So these are the given boundary condition values. So this is the system, the governing equation of elasticity. Well, using the shorthand notation, the index notation, we can write it in a very, very compact way. But if you take the theory of elasticity, to understand fully all these relationships, it may take more than half a semester. The first few weeks we focus on one relationship and discuss that, and the next few weeks and do things like that. But now we have to run, okay? So, all right. And last lecture we talk about that. We also talk about that. We kind of talk about that and that also. We have not gone through details about that. So let's do that this time. This is the section stress-strain relations. Let's first start with 3D, okay? For linear elastic material, it turns out there is a linear relationship between the stress component and the strain component. We express that in terms of a matrix. We call it the stiffness matrix. This is the material stiffness matrix, not, which is different from the element stiffness matrix or the global stiffness matrix, okay? Just to point that out. The relationship is this. Sigma x, and then sigma y, sigma z. So the three normal components, and then the three shear components, tau xy, tau yz, tau zx. Okay, and this is linked to strain component. Here we can write again all strain component. First one is epsilon x, and then epsilon y, and then epsilon z. And then we have three shear component. We can use the engineering expression, which is gamma xy. And by the way, gamma xy is also equal to twice epsilon xy. Okay? You need to remember that. The epsilon xy is what we call the tensor strain notation, tensor strain, shear strain. This is the engineering shear strain, okay? And the relationship between these two are just, it's just that this is twice of that. We said shear strain represents the angle reduction between two line elements that are perpendicular to each other initially or before deformation. So during deformation is reduced by that. The total angle reduction is gamma xy. If this is x direction, this is y direction. What about epsilon xy? It's half of that. Okay. All right, tau yz correspondingly there is gamma yz here, and then here we have gamma zx here. Again, you can write it as twice epsilon yz or twice epsilon zx. Okay, this is a vector. It has 6 components. That's also a vector. Therefore, this matrix must be 6 by 6. And it turns out for this 6 by 6, you can actually decomposed into 3 submatrices. First, that stiffness matrix is symmetric. And also, there are a lot of zeros. These 2 blocks, actually all the components are 0. And this matrix is diagonal only. Okay? And it is 1 minus 2 nu over G over 2. And nu is the Poisson's ratio. And then here is 1 minus 2 nu over 2. 1 minus 2 nu over 2. And then you have 3 zeros here. 3 here. Therefore, this matrix is diagonal only and all the elements are equal. The only thing that is more complicated is this one. It is a full matrix, 3 by 3, but itself is also symmetric. This becomes 1 minus nu, and then nu. 1 minus nu, and then 1 minus nu. And here is symmetric. So that is the stiffness matrix. And this is for 3D case, okay? And it turns out if this is reduced to 1D, where only sigma x is non-zero, all other stress components, sigma ij, are 0. That means this is non-zero, all these are 0. That is called the uniaxial loading case. So uniaxial stress. Stress case. Then this will be 0, and it will be simplified to the following relationship. Sigma x is simply, in front of that, I'm sorry, I missed a huge thing here. There should be a factor E times 1 plus nu, 1 minus 2 nu here. Okay? So don't forget that big factor in front of it. Okay, for the uniaxial stress case, it turns out sigma x is directly linked to epsilon x by that. And this is the well-known Hooke's law. Okay? And that coefficient E here is the Young's modulus. All right. When we express stresses in terms of strengths, the matrix, the coefficient matrix in front of the strengths is called the stiffness matrix, which is this one. But we can invert this and put it on the other side, right? Then that means we express strength in terms of stresses. Now, if we do that, we call it the compliance expression. Compliance matrix is as follows. Then now we have strengths on the left-hand side, so epsilon x, epsilon y, epsilon z. And then now instead of writing gamma xy, I will simply write it 2 epsilon xy, which is the same thing as gamma xy. And then 2 epsilon yz, and then 2 epsilon zx. Okay? This is equal to 1 over E, and then a 6 by 6 matrix. Here is sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. Let me check the video. Okay, this matrix, the coefficient is as this. Again, it can be partitioned into matrix, submatrix like that. Again, this is 0, 0. That means a 3 by 3, 0, 3 by 3 submatrix, okay? And then here, again, is diagonal. The coefficient is 2, 1 plus nu. And here is 2, 1 plus nu. And 2, 1 plus nu. And this is 0, 0, 0, 0, 0, 0. Okay, this is that part. And the upper left submatrix is again a full matrix. And here is 1, negative nu, 1, negative nu, and then 1. And negative nu here, negative nu, negative nu. Okay? So that's the compliance matrix. And again, you can see very, very clearly in 1D case, uniaxial stress, all these will be 0, only that one is non-zero. Therefore, this is equal to applying the matrix multiplication, these times this row and flip 90 degrees and put in the corresponding position, right? Only that one is left. Therefore, in 1D case, uniaxial stress, you can see very clearly epsilon x is equal to 1 over E times sigma x. And that's, again, a well-known relationship. The Hooke's law, we learned that in mathematics, right? And these two are the same thing, just the inverse of each other. Okay, this is the 3D matrix. What I like to emphasize is that for a 3D stress-strain relationship, is not as simple as stress divided by modulus give you strain. That statement applies only to uniaxial stress case, like this and that. When it is biaxial or 3D triaxial, it's not as simple as that. It is this. And the matrix is sometimes a little bit difficult to remember, but I can always remember this one. Okay? Because why can I remember that one very, very easily? For the shear strength, it means, okay, take the first one, 2 epsilon xy, that's the engineering shear strength, is equal to, using this expression, times tau xy. We learned that, right? What is this? This is, the inverse of that is exactly the shear modulus. So it is equal to tau xy over the shear modulus. And of course, we know engineering shear strength xy, gamma xy, is equal to engineering shear stress tau xy divided by shear modulus. Therefore, that one is very easy to remember, right? So you know that part. What about this part? If you express epsilon x and write that out, it becomes sigma x over E minus nu sigma y over E minus nu sigma z over E. And again, this is easy to remember because it says when you apply a stress sigma x in x direction, it generates stress in that direction, which is the stress divided by modulus. We know that, right? However, if I further apply stress in y direction, epsilon y will be sigma y over E. But because of Poisson's effect, there is shrinkage in x direction. What is the shrinkage? The shrinkage is negative Poisson's ratio times epsilon y. This is epsilon y. So negative Poisson's ratio times that means how much is strain when you put it this way, right? So that's easy to remember. So that will be just superimposed to whatever you have in x direction already. Similarly, that one means when you apply a stress in Z direction, you generate this much of shrinkage in X direction. So you add all these three together, you have the total strength. Therefore, this relationship is actually pretty easy to remember physically. Once you remember that, and you remember that, which should be very easy to remember, you have the whole thing. Okay? Because the second one, you just take care of the index appropriately. And this one, and then you have this whole. Once you have this thing, you invert it, you get that one. Therefore, I always advise you to remember this relationship. And as you can see clearly from that, once there's a non-zero Poisson's ratio, you can see that the normal strength in one direction is affected by normal stresses in all three directions. This one and this one and that one. Therefore, in general, you cannot have the case where epsilon z is 0 and also sigma z is 0. This is very difficult to achieve for an elastic material when the Poisson's ratio is not 0. Because when the Poisson's ratio is not 0, there is general non-zero stress in the body. Even if in the z direction there's no normal stress, there will be normal strength in z direction. This is in x, okay? So if I write it epsilon z, this is sigma z over E, nu sigma x over that minus nu sigma y over that. Okay, let's talk about this. If we talk about this is x, this is y, this is out of plane. If sigma z in the thickness direction is 0, epsilon z is still non-zero in general. Okay, therefore you cannot have that at the same time. But you can have, it's very easy to have gamma xz to be 0 and also tau xz to be 0. In fact, if this is 0, tau xz will be 0 because it's linked directly. And again, gamma yz, if it's 0, then tau yz is 0. Okay, now we run into the problem that when we say we apply biaxial stress, and the out-of-plane shear will be 0. Then the shear strength will also be 0. However, the out-of-plane strain is not 0. Therefore, we cannot really choose, we can never have a pure 2D stress case, strain case. I should put these two together. If the stress is 2D, the strain will be 3D. In fact, even for 1D case, uniaxial case, you can only say uniaxial stress. Strain is actually 3D because of shrinkage in the two lateral directions. Or you can say uniaxial strain, but the stress will be 3D. You have to constrain the two sides when you put it, and you only have that direction strain. But because of the constraint, you fix the two directions of the material, it will generate stress in this direction and that direction when you put it this way. Okay? Therefore, now, for a material that has non-zero Poisson's ratio, if nu is not 0, you can never achieve true 1D case or 2D case. Everything is actually 3D. But you can only talk about stress being 1D or stress being 2D. Then strains are 3D. Or you can talk about strain being 1D or strain being 2D, but stresses will be 3D. Okay? That actually leads into our next topic, which is plane stress and also plane strain. Alright, because I need a space here, I need to erase that. Plane string case. Plain string case is this. All the out of plane strings, out of plane means z direction, okay? All out of plane strings are 0. Therefore, epsilon xz is equal to epsilon yz is also equal to epsilon z equals to 0. This is called plane string. What kind of situation you will have string, plane string? Well, when you have a very thick let's say you have a dam that has a uniform cross section, okay, like that, and pressures from water acting on one side throughout the thickness. And this is z direction, this is x direction, this is y direction. And in case like that, you have plane string situation. These things very, very long. The two sides are fixed. Now you take any slice of the cross section. There's no reason for any slide to move to the left or to the right. Okay? Therefore, the z displacement will be 0. They will remain plane. So any cross section, the deformation is always in plane only. It will not move to out of plane. Because of that, immediately you can see the shear strength that contains a z index will be 0. That is plane strain. All right, for plane strain, if you look at this expression, it means this guy is 0, this guy is 0, this guy is 0. Okay? Now, because of that, these three numbers are always 0. We can effectively cross the corresponding columns and rows when we do the multiplication. Okay? Therefore, now, if you look at sigma x, these will play no role at all because these will times 0 all the time. And also, these two numbers will times these two zeros all the time. Therefore, sigma x will be equal to this times that, plus this times that, plus that times that. That means we can reduce the 6 by 6 matrix by a 3 by 3 relation. Okay? Therefore, now I can write these out as 6 by 6 is reduced to a 3 by 3 relation. It is as follows: sigma x, sigma y, and then tau xy is equal to e over 1 plus nu, 1 minus 2 nu, and here is 1 minus nu, nu, 1 minus nu, 0, 0, 0, 0. And here is 1 minus 2 nu over 2, and then times epsilon x, epsilon y, 2 epsilon xy. Okay. This is in fact a submatrix of that, of the 3D compliance matrix. The reason we can take the submatrix is these three numbers are 0 all the time. Okay. But then, don't forget the last relation, sigma z, because sigma z is not 0. So take this expression, you can see clearly that sigma z is equal to e, and then 1 minus 1 plus nu, 1 minus 2 nu. Then this times that plus this times that. Therefore we have nu epsilon x plus nu epsilon y. Okay. In fact, we need 4 relations for plane strain situation. Okay? And then, once we have that, we can then express strain. This is stress in terms of strains. We can invert the relationship and express strains in terms of stresses. That is called the compliance matrix. Therefore, invert the above relationship. We have epsilon x, epsilon y, 2 epsilon xy equals 1 plus nu, and then E okay. All right. I call this plane strain. I use epsilon to represent plane strain. So plane strain compliant matrix. This is plane strain stiffness matrix. Okay. And if you look at the compliance.
Do you have those backwards? Isn't stiffness stress in terms of strain and compliance is strain times
yeah.
stress?
I'm sorry. Thank you for pointing that out. Plane strain stiffness. Here is plane strain compliance. Very good. And the thing I like to point out is that if you look at plane strain case, the plane strain stiffness is a submatrix of the 3D stiffness. However, if you look at the plane strain compliance, it is not a submatrix of the 3D compliance matrix. I already erased that because I don't have enough room here, but you can compare that with the lecture notes that you have. Okay? So this is a sub-matrix of 3D stiffness matrix. This one is not a sub-matrix of 3D compliance. The reason that the compliant matrix is not a submatrix is if you look at the 3D compliance matrix for plane strain, 3 things on the left side of the equation is 0 all the time. But 4 things on the right-hand side of the stress vector is not 0. 4 non-zeros. So you cannot simply cross out the 3rd row. You have to invert this relationship to get that. Okay? So this is a very important point. All right. Now, as a comparison, let's do another case. So the plane strain is like a 2D strain case. Okay? Then we have 2D stress case, which is called plane stress. In a very similar fashion, we can talk about plane stress situation, which can also be called 2D stress case. And again, when it is 2D stress, strains are 3D. Okay? Let me simply write this out. When we express strains in terms of stress, it becomes this. 1 minus nu 0 minus nu 1 0 0 0 2 1 plus nu sigma x, sigma y, tau xy. This is the compliance, and the stiffness is the sigma x, sigma y, tau xy. E 1 minus nu square, 1 nu, 0, nu, 1, 0, 0, 0, 1 minus nu, and then 2, epsilon x, epsilon y, 2, epsilon xy. Okay? Alright, this is the plane stress compliance, plane stress compliance. This is plane stress stiffness. Okay, it turns out for plane stress situation, the compliance matrix is a submatrix of the 3D. So it is a sub matrix of 3D compliance. But the plane stress stiffness is not a submatrix, okay? Same reason, because when you look at 2D stress case, express things in terms of compliance, you have on the right hand side the vector 3 zeros all the time. You can directly cross the rows and columns and get a submatrix out of that. But when you express that in terms of stiffness, on the left hand side you have 3 zeros, but the right hand side you have 4 non-zero. You only have 2 zeros. So you cannot simply cross out a row, because you will have non-zero things times the coefficient. So you really have to invert that to get that, okay? So this one, you get it directly from 3D case and invert it to get the stiffness case. And as you can see, these two cases, they are just opposites of each other in terms of submatrix, okay? All right, for now, I will just say if you, I'd like you to focus on plane strain, because in our program, at the end, I required you to at least make the plane strain case work, okay? And it just takes a little bit of effort to add the plane stress case, but this is required and it's the default option. Therefore, this is important, remember that. And it would be nice to also remember that also, but it's not required. This is required, okay? All right, now I have reviewed the governing equations of elasticity, all three types of relationship. One is equilibrium, sigma ij comma j plus bi equals 0. That represent three equations. The second one is called the kinematic or geometric or strain displacement relationship. That is epsilon ij equals half ui comma j plus uj comma I. Okay, so that's the kinematic. The third is called constitutive law or the physical relationship or material relationship. Sigma ij times Cij KL times epsilon KL. That's a long, a contracted shorthand notation. When you express that in full, is the 3D first, and in a special case, in 2D case, it will be this and that. Okay, and then we have two boundary conditions, two types of boundary condition. One is the essential boundary condition. Displacement are described. The other one is natural boundary condition where tractions are described. Okay, all the equation I will talk about last lecture up to this point also, they are called the strong form of equation. Why is strong form? Because it is in partial differential equation form, it means when you write those equations at the very, very beginning, you should write for any generic point, okay, an arbitrary point, the following equations hold. So that means this set of equations applies to every single point of the domain. That's a very strong statement. Every single point. All right, and then we know that there is, for governing equations, there is another form which is called the weak form, right? We spent first few weeks elaborate on that. Okay, then the question is, how can we change this strong form of elasticity equation into weak form? That's what we are going to do next. We can also say the weak form is the finite element form, okay, formula. Because we use weak form in our finite element program. We start with the equilibrium, sigma I, j, comma j plus bi equals 0. And again, let me emphasize that these j are dummy indexes because it appears twice. It means summation. It really means this. Summation sigma ij, and again this comma means partial differentiation. So I should write it as partial sigma ij partial xj plus bi equals 0. So this expression actually means that. Okay. All right, we start with that. And then what we are going to do is, remember what we do with governing a partial differential equation? We take a weighting function times that and integrate over the problem domain and require that to be 0. So in a way, we say, okay, instead of requiring every point to be 0, now we says as times a weighting function average over the domain, the whole thing should be 0. Okay? All right. Therefore now we say this is weighted residual. Well, when we use weighted residual, in principle, any weighting function is eligible as long as the weighting function satisfies the essential boundary condition. That's the only requirement. Okay. Now, which weighting function should we use? It turns out, for this one, if we use the displacement field, it will be a very good way to do it. And the displacement field itself is the solution we are seeking. So in a way, once you use the solution as the solution field as the weighting function, that's called the Galerkin's method. Therefore, using the Galerkin's method, sigma I j comma j plus bi. This time we're going to times an arbitrary variation of the displacement field, okay, and integrate it over the problem domain. This time we are talking about 3D, so it is the total volume of the elastic body. We require that to be 0. What is this delta ui? This delta ui is called a And that is a small variation of the displacement field. We can also give it a name called the virtual displacement field. Okay? So we effectively change a strong form of governing equation into a weighted residual. Okay? It's not the weak form yet. Remember, for weak form, we need to reduce the differentiation on this part and increase the differentiation on the weighting function. So that's what we are going to do next. Let's then expand that. So this times that, of course, we can write it as sigma ij, comma j, delta ui plus bi delta ui, and then dv equals 0. Okay? Now let's focus on this term here. First term, which is equal to sigma ij, comma j, delta ui, integrate over the volume. We can write it as this. There is a differentiation here. If you write it as sigma ij, delta ui, times together, and then differentiate it outside, that means two things times together and then take differentiation with respect to xj. And of course, that operator will act on the first term first and times that. And then you will also act on the second term. But here we only have the first term. Okay, this first term is exactly that. So we still need to minus the second term, sigma ij, delta ui, comma j. Then these two will become an identity. Because when you expand that, you will have two terms. The first term is exactly that. The second term is that with a plus sign, not the minus sign. So the second term will just cancel that. Therefore, this is equal to that. Okay? And then now, let's look at this one. Sigma ij, delta ui, comma j. Let me write it as half sigma ij, delta ui, comma j, plus half sigma ij, delta ui, comma j. Of course, that's okay. One thing is equal to half plus half of itself, right? But then, the first term I will keep. The second term, I'm going to do something. I'm going to change these two indices. I flip these two. So I write it as ji and then delta ui, comma j. That is okay, because we know stress components are symmetric with respect to its index. Whether you call it sigma ij or sigma ji, it's the same thing, right? So that is no problem. Because sigma ij is equal to sigma ji. All right, so that will be equal to now sigma ij delta ui, comma j plus now half. Okay, next, I'm going to do something else. Because of symmetry, this is equal to that. But now, these j's are dummies. These i's are also dummies. They indicate summation from 1 to 3. Therefore, whether I call it j or I, whether I call it j or k or any other thing, it will not affect the result. So I'm going to call this sigma k, okay? So this is I. delta ui comma k. That's the same. And then I write that, and because I can do it, I can also call this sigma k. Now I'm going to, these i's are also dummy. I can call it j if I like. Okay, if you are a little bit doubtful about that, let me tell you, if you have ai, bi, where I is from 1 to 3, is exactly equal to a, k, bk, when k is equal to 1 to 3. We know the index just serves as a dummy row. At the end, it will not affect the end result. So whether I call it I or k doesn't matter. Therefore, that's why I call this j here k first. And then I call this I here j. Okay, at the end, I can now call k I again, u, j, and then I. The reason I want to do this, go this rounded way is I cannot directly call this I here because I call it I, it will interfere with that I. It will cause confusion. Okay? So if I can change to any other index but I here. So that's I what I go here. And then next I want to go like that. Alright, at this point, this is that, this is equal to that. Now I can take sigma ij out because sigma ij is the same. Okay, then I have half left, and then here is delta I comma j plus delta u j comma I. There's a reason I want to do this with these indexes. Sigma ij. This delta thing acts very similarly as a differentiation, like a d, dx. So you can take that out. It's delta half ui comma j plus uj comma I. What is this? Half ui comma j plus uj comma I.
String.
Exactly, it's shear, exact string epsilon ij. So sigma ij, and here is half epsilon. Oh, the half also go away because half together is called a string. So epsilon ij. All right, so I go into a very detailed and then show that this thing is simply equal to that. Okay? Therefore now I can write this term because of the derivation here, and this term becomes sigma ij delta ui, the whole thing together, comma j, minus this. Okay, this is equal to that, so it's sigma ij delta epsilon ij, and then integrate over v with respect to v here, also with respect to v. Okay? Yeah, I would say C derivation on right there. Then at the end I have that. Now because I have only limited space here, I need to use that. So let me erase this. Alright, at this point, I'm going to do something further. Okay? This thing, second term here, is equal to a function. I can view these two terms times together as a function. Okay? So this is a function, and then comma j. So one thing inside, and then comma j, and then dv, which means partial this thing with respect to xj and then dv, and integrate over the whole volume. And now, if you remember the Gaussian theorem, this is integration of the divergence of that function over the volume. The Gaussian theorem says if you have a function, you calculate divergence every point inside the volume and integrate that, is exactly equal to that function times the integration of the function over the surface. Okay, but only the normal component will contribute, which means this thing times the normal component with respect to that, and then dv. Which means what I inside the bracket is this guy. So is sigma ij delta ui and then nj and then dv. So this is using the Gaussian theorem or the divergence theorem, okay? We have that. And then, now, if you look at this expression, we can do something else. There is a sigma ij here times delta u and then times nj. If we change the position, it will be sigma ij nj and then delta ui dv. Okay, what is that? Sigma ij nj will be equal to the traction, right? So is traction. We use Ti to denote that. This is the traction. Delta ui dv. Okay. Well, I should say this is the surface. Okay, the total surface. To be more rigorous. This is a volume integral, now it is a surface integral. Alright, so this is the whole surface of the body. Yes?
Is that traction Ti or Tj?
Ti, because on these two, sigma ij and nj, the summation is on j. So what is left? The free index is I, so it's I. And also that free index corresponds to that free index. So there's another summation. So it should be Ti. Alright. And then what I like to say is this is a surface integration over the whole body. The whole body, the surface, the whole surface consists of two parts. Essential SU and then also ST. So I should really write it as U plus ST, okay? Then the same integral, delta ui dv. However, we said any weighting function must vanish on essential boundary condition for it to be eligible as a weighting function. Okay? Therefore, when the integration is over the essential boundary condition, delta ui is 0. Okay? Therefore, this then is equal to st ti delta ui and then dv only. I would say because delta ui equals 0 on SU. The weighting function must be 0 on essential boundary condition. So the integration at the end only is non-zero on the traction boundary condition. Okay? Alright, now when we put everything together here, this is equal to that, which is at the end, let me see here. This